So our last section in chapter 4 and our fifth skill is learning about oxidation reduction reactions. A lot of chemistries happen because we have the net movement of electrons from somebody who has a lesser attraction and wants to be oxidized or lose their electrons, and they give them up to somebody who has a greater attraction for electrons, or they become reduced. So however you learned about redox chemistry, maybe it was Leo the lion says grr, lose electrons oxidized, gain electrons reduced, or maybe you learned oil rig, oxidation is loss, reduction is gain. However you want to remember it, you do want to have committed to memory that if something is oxidized, it loses electrons. If something is reduced, it gains electrons. Similarly, some confusing kind of nomenclature can come when we talk about agents of reduction, so reducing agents or oxidizing agents. If you want to just memorize that it's the opposite, that's fine, but I think it's easier if you understand why. Something that's a reducing agent, it forces somebody else to be reduced. It forces somebody else to be reduced and gain electrons. Well, how it does that is it becomes oxidized itself. So something that's a reducing agent is itself oxidized. Conversely, something that's an oxidizing agent forces something to lose electrons. It does so by taking them on itself. It becomes reduced. So nomenclature that we have to make sure that we understand. And maybe new to this chapter is the idea of assigning oxidation numbers. So assigning oxidation numbers is really the, or we call the oxidation state of an atom, is really thinking about what the charge would be on the atom if we pretended that it's an ionic compound. And I know that's a little bit confusing, but we're going to assign it oxidation numbers for things that are covalent compounds. But what you need to do is pretend one species is cationic and one's anionic and treat them as though they were anions. So we'll have lots of problems that we'll practice to assign oxidation numbers. And why it's important to be able to assign oxidation numbers is when we do chemistries, if you see that oxidation numbers change, we know that redox chemistry is going on, and importantly, it'll be able to identify who's being oxidized and who's being reduced, because those are the kinds of questions you're likely to see on exams. Okay, so let's go ahead and just kind of start this, and we're going to start with sample problem 4.9, which gives us 4 compounds, and we need to determine the oxidation number for each element in these species. So it's fairly easy when we have ionic compounds, which is what we're going to see with these this first example here. With ionic compounds, you just consider the fact that they're ions. I should point out too here that table 4.3, not a table that you'll get. Table 4.3 gives us rules for assigning oxidation numbers. And so let me just read through these rules first before we start this. If something is in its elemental form, the oxidation number is 0. If it's a monatomic ion, okay, we have an ionic compound, the oxidation number is just the charge on the ion. So that's really simple. If we have polyatomic ions, we need to consider the sum of all charges. So our second problem that we'll have here is a polyatomic ion, so I'll kind of go over that. But our first problem here is pretty straightforward. When we have zinc chloride, what we have is zinc 2+ cations and then chloride anions. So the oxidation number, and how I like to do this just to introduce you to the formalism that I use, I always like to write the oxidation number on top. And when we have charges for ions, it's obvious that that's what it is. So the oxidation number for zinc is 2+. For chlorine, it's -1. So fairly easy. So kind of the easy problems is when we have ionic compounds, because it's simply the charge. So that's pretty straightforward. So monatomic ions, it's just going to be the charge. Okay. The next problem, we deal with a covalent compound, sulfur trioxide, so SO3. And remember in chapter 2, when we learned how to write and how to name these, we always kind of wrote the species that was more cationic-like on the left, and the more anionic-like species is on the right. And so what we do is we treat oxygen as though it were the anion. And one of the rules that we have down here for oxygen, the oxidation number is always going to be -2 unless you have a peroxide. We don't have a peroxide here, so the oxidation number is -2. So again, here's how the formalism works when I write these problems. I write oxidation numbers above. we need to consider the total amount of charge that comes from every atom having that oxidation number. So down here below, I write a little bracket, and I say -6, okay? Because the oxygen, 3 of those oxygens is going to contribute -6 to our charge. The entirety of this species has to have a charge of 0. So I bracket my entire species and I write a 0. That tells me that my sulfur has to contribute a +6 charge. Because there's only one of them, my oxidation number is also +6. So again, I'm going to use the same formalism as we go through the rest of these. So hopefully this will make sense. Okay, so let's work through our next problem. Nitric acid, HNO3. Again, you got to know from Chapter 2 in acid nomenclature that that's what nitric acid is. So I'm going to show you 2 ways to solve this. The first way I'm going to show you kind of treats it as though we have an ionic compound here, something that dissociates. We've got H plus and then NO3 minus. Okay, when we treat this as H plus, the oxidation number for hydrogen is +1. Here's how we treat polyatomic ions. Again, I know that oxygen is always going to be -2, so my contribution from oxygen is -6. This polyatomic ion has a total charge of -1, so that must mean my nitrogen is contributing +5. Since there's only one of them, the oxidation number on nitrogen is +5. I'm going to show you that you could get the same answer for this problem by keeping everything together and using the same formalism. Oxygen is always going to be -2, -6 from that contribution. Hydrogen is always going to be +1. Contribution is +1. This is a neutral ionic compound, so the total of this is 0. That must mean my nitrogen is +5. There's only one of them, so the net, or the oxidation number for my nitrogen is +5. So do you see how you could work that one the same way, whether you break it apart into its ions or you leave it together as a neutral compound? Either way works, whatever makes most sense for you. The reason I broke it apart into ions is because for our last one here, we actually have to consider the fact that dichromate is a polyatomic ion. So dichromate is Cr2O7 2-. So again, treating this the exact same way I've treated these other problems. Oxygen is always -2 unless it's a peroxide. There's 7 of them, so that contributes a total of -14 from my oxygen. The total is -2, which is again the same as my charge on my polyatomic ion, which means my chromium's behaving as a cation must contribute +12. Since there's 2 of them, the oxidation state on each of those chromiums is +6. Okay, this one, since it might be something new, might be one you want to rewatch again. But again, that's important to assign oxidation numbers, because as we move on to our next problem and actually look at redox reactions, we need to compare oxidation numbers to see if redox chemistry has happened.